हेलो। हेलो।
Şu. Cesedi de ver. No, 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 no. Mm. Ya tu, tu, tu. Oh,
Good evening, sir.
Good evening, sir. Welcome, Suresh sir. Welcome. Good evening to everyone. Good evening to everyone. Vipin Saran sir, good evening. Lakshman sir, Saket Ghosh, Ramachandran. Vipin Saran sir, good evening. Welcome.
Good evening, Mr.
Okay.
Selvaraj and everyone.
Yes,
Good
sir.
evening.
Welcome.
After a long time, I was
Yes,
extremely
sir. Thank you. Thank you for
engaged.
joining. Yeah.
Yeah.
Just silent movie, 1 hour. Okay. And Tata is busy with the don't make sound. If you make sound, I'll close it. Hello. I'm going to close it. If you make sound, I'll close it. I'm disturbed. I am disturbed. இல்ல தெரியும் ஒன்றும் பண்ண முடியுமா
Good evening, sir.
Yes, sir. Good evening, sir. Welcome.
Good evening, Suresh, sir.
Good evening, sir.
So, Sangha, good evening. Welcome.
மாநிலத்தின் பல பகுதிகளில் டிட்வா புயல் காரணமாக
Good evening, Dr.
Yes,
Salvaraj.
sir. Good evening, sir. Welcome, sir. Welcome, sir. Good evening, sir.
Good evening, good evening.
Shall we start, sir? With your consent, we will start, sir.
Yeah, no problem. எனக்கு அந்த ஷேர் மட்டும் கொடுங்க permission. Share
Share
permission.
rights are given to you. Already rights are given to you. You can share it and you can try.
Yes, sir. Permission is given, sir. You please check your PPT, sir.
Okay. இதுவா?
Screen, sir. Screen. Enter screen correct தான், sir. இப்போ மினிமைஸ் பண்ணிருங்க சார். அதில் மை கம்ப்யூட்டர் சார். NW PPT.
Now, can you able to see my screen?
Yeah, we are able to see, sir. Yes, sir.
Okay.
Good evening, Bala sir. Welcome to the session.
Good evening, sir. Good evening, sir. Thank you, sir.
Right, sir. Thank you, sir. We will start the program, sir. Okay? With your
Yes, sir.
consent. Yeah. Happy good evening to everyone. Today we have an interesting topic, that is high performance and high productivity technologies for joining emerging materials. It's going to be delivered by the eminent professor, Dr. V. Balasubramanian sir, ME PhD, IIT Madras. He is a professor and director, Center for Material Joining and Research, that is CE major shortly called. It is a Department of Manufacturing Engineering, Annamalai University, Sidambaram. First of all, we thank Dr. V. Balasubramanian sir for readily accepting an invitation to deliver a talk in this emerging talk, the high performance and high productivity technologies talk. Thank you, sir, for joining in our platform today.
Thank you.
The Institute of Indians, in association with the Institute of Indian Institute of Welding, that is other professional bodies, the Indian Society of Non-Destructive Testing, and we used to conduct this program for the past 3 decades. We can say it is from 1992 onwards. We have done more than 17-12 programs so far, and after the pandemic, we switched over to this virtual mode. Virtual mode also we made around 3-10 programs like that. Our aim is to propagate the emerging technologies to our members, students, faculties, and to the society at the large. Our boundary, insurance boundaries from Arilur, Perambalur, Karur, Pudukkottai up to Nagapattinam, whereas Indian Institute of Welding is down south, and the Indian Society of the Non-Destructive Testing also down south. We have our own office at BHL 3000 acres campus, which was given by the great Kamaraj, our former Chief Minister of Tamil Nadu. And we have our 100 seating AC lecture hall and 300 seating one conference room, one library with 4,000 plus books, and other amenities are there. So with this brief introduction about activities, I call upon Dr. Kevin R. Kumar, the present chairman of Institute of Engineers, to proceed over and welcome the gathering. Over to Dr. Kevin R. Kumar, sir.
Good evening to all the dignitaries. So on behalf of the Institution of Engineers India, Tiruchirappalli Local Center, it's my pleasure to welcome Dr. V. Balasubramanian, Director, Center for Materials Joining and Research, C Major, Professor, Department of Manufacturing Engineering, Annamalai University, Chidambaram, and Vice President, South, the Indian Institute of Welding. Sir, it is our great honor to have a wonderful chief guest and speaker like you, and we take this opportunity to welcome you, and it will be a very good session for our people, those who are joined here. At the same time, I would like to welcome all the senior faculty members of various universities, past chairman of the Institution of Engineers, Tiruchirappalli Local Center, and the corporate members of Institute of Engineers. So, along with the Indians of Building and IIM and NDT and various other forums of BHL located within BHL campus, I welcome you all. So, I kindly request all the participants to take part in this lecture program, and I kindly request you to interact with our today's speaker. He is a well-versed speaker, and he has got wide knowledge in the area of welding, and he has closely worked with the majority of the university and industries like BHEL, etc. So I request all the participants to make use of this opportunity and to interact with them. And with this short introduction, short address, I welcome you all once again. Thank you.
Thank you, Dr. Kevin R. Kumar, for presiding over welcoming the gathering. Now, moving on to next agenda, I call upon Engineer L. Ramachandran, Honorary Secretary, also Scientific Officer for Baba Atomic Research Center, this BHL customer, to introduce today's chief guest to the participants. Over to Dr. Engineer L. Ramachandran, sir. L. Ramachandran, please.
Good evening, one and all. Rajesh, can you please switch on my video? Give permission. I'm here. Yes. Good evening, one and all. Welcome, sir, for the today's evening session. I'm here to give a brief introduction about Professor V. Balasubramanian, sir. Dr. V. Balasubramanian, sir, is working as a professor of manufacturing engineering and director, Center for Material Joining and Research. It's in short form C Major, Specific Faculty of Engineering and Technology, Annamalai University, Chidambaram, Tamil Nadu. He's a graduate from Mechanical Engineering from Government College of Engineering, Salem, University of Madras in 1989. He has completed his Master's Production Engineering from College of Engineering, Guindy, Anna University in 1992. He obtained his PhD Metallurgical Engineering from Indian Institute of Technology, Madras, IITM, Chennai in 2000. He has a long experience in teaching, 33 years, and 30 years in research experience, which will be a rich thing which we are going to, he will give a lot of experience to us, we'll share. He was promoted as professor on April 2005, and he served as the head of the department, manufacturing engineering, for 3 years in 2019 to 2021. He served as Directorate of Research and Development for 1 year during 2021. He served as director. He is serving as a director C Major since 2016 for the last 10 years. We have listened a lot of things from sir. Again, we are here to listen to the latest, what is going in the welding field. His area of research interest are material joining, surface engineering, processing of advanced materials. He has published more than 500 papers in Scopus Index Journal, and his H index is 66. He has supervised 30 PhD scholars, and again, another 5 scholars are with him. So will be, if anything new we want, we can ask him, so that he'll be able to do a research and tell us, and we can use his experience. He has completed 45 R&D projects worth 15 crores from various organizations: DST, DRDO, ISRO, DAE, ICE, ACTC, it's a long list, implemented another 5 R&D projects worth rupees 10 crores. He was ranked in the top 2% scientists in world and 9th ranked in the materials from India, ranked by Stanford University into USA in 2021 to 25, 6 consecutive years. He has established a Center for Metal Science, Metal Joining and Research in 2008 under AICTC scheme, and it houses many state-of-art facilities for testing and doing research. He was a coordinator for UGC SWAP, deputy coordinator for UGC Innovative Program, deputy coordinator for DST, FIST Level 2 schemes. He has designed curriculum for MTech students for nanomaterial and surface engineering, offered UGC Innovative Program, and ME Welding offered with financial support of industry. He has visited various countries like Singapore, Hong Kong, Canada, USA, and he has presented more than 100 papers. He has given a lot of keynote address, expert lecture in various institutions and industries. He has worked as a visiting scientist from under Science Research Fellow Scheme from Memorial University of Newfoundland, St. John's, Canada, and 4 months, May 1999. He has worked as visiting professor in Center of Excellence for Advanced Material, University of California, USA for the 3 months. And his students have presented more than 400 research papers in national and international forums and seminars. His students have won more than 25 Best Paper Awards. It's a feather to his cap. He has organized more than 50 programs of conference, seminars, workshops, FDP program for the benefit of scientific community and the other teaching communities. He received Distinguished Research Award from Annamalai University in 2005, Professor Placid Rodriguez Memorial Lecture Award from IIW 2010, Professor D.R.J. Acharya Distinguished Academician Award from IWS, and Keithworth Hurt Memorial Lecture IIW 2022, A.K. Seal Memorial Lecture Indian Institute of Metals 2025. He is an expert member in many committees under DRDO, ACRB, DST, National Board of Accreditation, and member of Academic Council and member of Senate of Annamalai University. He is a life member of IIW, IWS, ISTE, and IIM. He was the chairman for IIW Chennai chapter for the last 3 years from 2020 to 25. And presently is the vice president of IIW Southern region. And with his guidance, I think IIW will grow in the Southern region. He has taken a lot of initiatives. Recently, he received Halil Kaya Gethwick Award 2025 from IIW in 78th Annual Assembly of IIW held at Genoa, Italy on 22nd June 2000 from the outstanding contribution in the field of welding science and technology. He is the first Indian to receive this award. He deserves this. With this brief introduction, I welcome you, sir, for this session. The session is for you, sir, for the next 45 minutes. And next.
Thank you, sir. Thank you. Yeah, so thank you for your exhaustive introduction, Sri Ramachandran sir. And also, I thank Dr. Selvaraj, former Deputy General Manager, Bharat Heavy Electricals Limited, Trichurapalli, for inviting me to deliver this technical talk or technical lecture under the banner of Institution of Engineers India, Trichurapalli Local Center. I thank all the office bearers and the professional bodies involved in this because now they are continuously doing every week, whether every Tuesday evening 6 to 7 or 7:30, they are making available of some experts in this line, no? So they invited me. Thank you for inviting me. So when Dr. Selvaraj contacted me some 2-3 weeks back, so he asked me to deliver the lecture, which I delivered some 3-4 months back in Kalpakkam in the National Welding Meet. So he told it was a very nice lecture, informative lecture. Same lecture you can deliver for the benefit of our audience through online. So with this request, now I have framed this topic: high performance and high productivity technologies for joining emerging materials. So the slide is moving.
Yeah, sir. You have to come, sir. Slide you have to present, sir. You again share it, sir.
Okay.
Now we are gallery mode. You have to.
Okay. Anand. 1 minute.
Yeah, we'll wait, sir.
Sir.
Okay, 3 people, man.
Sir, இப்போ slip show.
Is it visible now?
No, you have to come, sir.
Try to go.
ஷார்ப் இல்லை சார் இது மினிமைஸ் பண்ணிருங்க சார் கூகுள் போங்க சார்
Google.
ஜூம் சார் நீங்கள் கூகுள் க்ரோம் வந்து சார் ஓப்பன் பண்ணிங்க சரி இந்த கிளிக் பண்ணிக்கிறோம் சார் ஓகே சார் ஷேர் என்டையர் ஸ்க்ரீன் ஷேர் சார் ஓகே சார் இப்போ இதை மினிமைஸ் பண்ணிடுங்க சார் பிபிடி slide shows. Okay, sir. Okay, sir.
Yes, sir. It has come, sir.
Just to see, it's moving.
Yes, sir. It's
moving.
Okay. Thank you. So the agenda for today's lecture is, I just want to cover some 5 processes that was relatively new. I cannot say it is very new, but relatively new compared to other processes. One is on the gas tungsten constricted arc welding, GTCAW. It is also known as the interpulse TIG welding. The other one is on MIG welding. It's rotating arc gas metal arc welding. So it's another variant of gas metal arc welding process. Then third one is many people talking about CMT, cold metal transfer arc welding. Then a lot of work has been done here at the Annamalai University on friction stir welding, FSW. And then finally, I'll give some glimpses of solid phase diffusion bonding process. And finally, 1 or 2 minutes about my center, brief profile about my center. This is my agenda for today's lecture. So the first process is gas tungsten constricted arc welding. It's a relatively new process in the TIG welding. So you all know that it's the TIG welding is known for you all know that the TIG welding is a high quality process and it's a clean process, and though it is a high quality and clean process, it is good for thin sheet welding, not for the thick sheets or thick plates. And it's a non-consumable arc welding process. This is the diagram, which is you all know that. So you have a tungsten electrode. Through that, the current will be passed, and between the electrode and the workpiece, the arc will be established. Then you need to supply the filler rod in the arc column to melt the filler rod. If the thickness is higher, thickness of the sheet is higher. If the thickness of the sheet is thin, less than 3 mm, for example, that's some rule. If it is less than 3 millimeter, then you don't need to use the filler rod. If the thickness of the plate or sheet is greater than 3 millimeter, then you have to use the filler rod. Addition is required. So this is a very good process for many applications, but there are some limitations in this process. This is very slow speed process and high heat input. Because of the slow speed, the heat supplied by this process to the materials to be joined is high comparatively. Because if you take the heat input calculation, voltage into current divided by the welding speed. So welding speed is slow here. So the slow welding speed means high heat input is involved. So this high heat input and also the arc column is wider. The arc column is a bell-shaped arc column you will get in the TIG welding process. So the energy density, heat concentration is on a larger area. So because of the bell-shaped arc column. Because of this combined effect, arc shape of the arc and also the current supplied is, you have limitation in supplying the current also because you are supplying the current through the tungsten electrode and there is some limitations in supplying current through the tungsten electrode. So this completely causes a shallow penetration. Penetration is not deeper. Because of these reasons, slow speed, shallow penetration, this process is considered to be one of the low productivity process. But even though it is a low productivity process, slow speed process, for welding, critical materials or reactive materials such as aluminum alloys and magnesium alloys, even for titanium alloys, this process is preferable than the MIG welding process and other processes. So here, this is the left side. I am showing the constant current welding. So in the constant current welding is it's a conventional TIG welding process. In the conventional TIG welding process, the current is fixed. So based on the thickness of the plate, you are fixing the current, and the current is supplied continuously until from the beginning to the end. Suppose you are fixing 200 ampere, the 200 ampere current is supplied throughout the welding cycle, welding process. But it is not required to maintain the current at higher level. They found that so because the welding involved different stages, it's involved. The first stage is current is passed through the electrode, tungsten electrode, which is the non-consumable one. And this electrode and the short circuiting, because of the short circuiting, the arc is established. Once the arc is established, you are introducing the filler rod into the arc column. The filler rod melts. Okay, the filler rod melts because of the influence of the arc. And when it melts, it melts the molten metal from the filler rod to the molten pool. That's a weld pool is in the form of drops, molten droplets. So it is a transfer. The metal transfer takes place in the though it is a whether it is used as spray transfer or globular transfer or dip transfer, whatever the mode, but effectively the metal transfer from the tip of the rod to the weld pool is drop by drop. So the the once the filler rod melts and the molten droplets forms and it grows. When it grows, the surface tension force increases, but the surface tension force decreases, but the gravitational force increases. When the gravitational force overtakes the surface tension force, the molten droplet will get detached from the tip of the filler rod. So once it is detached, then it is on its own gravitational force, it is transferred to the weld pool. This is happening stage by stage, but it is all happens in the microseconds. So what the power source manufacturer decided to reduce the heat input in this process, they want to use a pulsing current, the current varying from maximum to minimum. So by that, the pulsing current is come into play. So how this pulsing current works? It is, um, yeah, the pulsing current in the pulse current welding. If you see the arc is fluctuating. Okay, why it fluctuates? The arc fluctuates. The current is varying from maximum current to minimum current. So you required maximum current to melt the filler rod or the electrode. And the once it is molten droplet is formed, and when it is transferred to the weld pool, during that time, it's a few microseconds, and the current can be reduced to lower level. But you should not reduce that to the zero, because if you bring the current to zero, then the arc will extinguish. So you should not allow the arc to extinguish. Arc should be maintained. At the same time, the heat or current should be reduced, and by reducing the current, the heat input can be reduced. So again, once the motor droplet is transferred to the weld pool, again raise the current, increase the current, bring to the higher level, and then in the next cycle, again it melts the filler metal again. Like that, it is happening. That's why you are seeing that the arc is fluctuating in the case of the pulse current welding process. So what happens here? There is a pulsating action between the pulses. The heat, the current also varying from maximum to minimum, maximum current, peak current to base current. Because of the variation in the current, the heat input also fluctuating. And not only that, there is always surrounding the arc, there is electromagnetic force. That force is also fluctuating from maximum to minimum. So current fluctuates from maximum to minimum. Heat input fluctuates from maximum to minimum. The arc force also fluctuates from maximum to minimum. And by the temperature also fluctuates from the temperature of the weld pool is also fluctuating from maximum to minimum. So these fluctuation, all this combined together causes the refinement in the grinds. Grind refinement is taking place in the pulse current welding. This process is preferable for the hard cracking susceptible material like aluminum alloys and titanium alloys. A lot of work has been done, and it proved that there is a grind refinement is taking place in the weld fusion zone. That grind refinement enhances the mechanical properties. So this is about pulse current welding. The another form of pulse current welding is, as I told in the beginning, if you see this schematic diagram, this is one arc is inverter arc. The other one is interpulse arc. Interpulse arc is nothing but constricted arc, gas tungsten constricted arc. So inverter arc is conventional TIG welding arc. So in the conventional TIG welding, as I told earlier, the arc is a bell-shaped arc. So it covers larger area. It heats larger area. When it's the heat that is supplied by the arc is distributed to the larger area. So when it is distributed larger area, what happens? You will be heating larger area, and that produces the net result is shallow penetration. But if you are able to constrict the arc, okay, by some means, then the arc can be narrowed down, and that the arc becomes the stiff arc. Once it becomes narrow arc, the area under the arc is greatly reduced, and the deeper penetration you will get in this process. Because the fusion welding, especially the fusion welding process, the process which produces very narrow weld zone or fusion zone is preferable. Okay, and also if you reduce the fusion zone size, weld zone size, then subsequently the heat up zone size also will be reduced. So in this process, gas tungsten constricted arc welding process, it's also known as interpulse TIG welding process. They are using superposition of high frequency waveform on the main current. So you have main current, that's a maximum peak current, and the base current similar to the pulse current welding. By superimposing the waveform on the current, you can restrict. So this is working based on the principle of so if you supply a current through a tungsten electrode, and the tungsten electrode conducts the current surrounding the tungsten electrode, there is a magnetic field. That magnetic field is constricted or restricted by the another current, superimposing of another current waveform. By compressing that, the arc become narrow in this technology. So this is a patented process developed by the vacuum and bracing company, VBC. That's a vacuum and bracing company, UK. They have developed, invented this process, and they have patented this process. And in this process, main parameters are, apart from the current, main current and the base current, you have delta current. The delta current is nothing but the current which you are superimposing on the original main current, and delta frequency, how much time it acts on that. So you can go up to 20,000 hertz. That means 20 kilohertz. The frequency will vary from 0 to 20 kilohertz also you can get. So by doing that, what happens, the arc width is 2 mm, it's reduced to 2 mm, and the arc remains constant even well below 0.5 ampere. So that is the advantage of this process. Even at low current, and the arc can be controlled, and you can weld very, very thin sheets with minimum heat input. That is the advantage of this process. So there are different modes are available in this process. If you want to weld then you have to go for the high penetration mode. In this, the interpulse current, which is the superimposed current, interpulse current is nothing but superimposed current, that is lower than that's a delta current, is lower than the main current. If you use this condition, then you will get the deeper penetration. But at the same time, if the delta current, the interpulse current is greater than the main current, then you can do for the surface modification like cladding, hot facing. Also, you can do for structure buildup. They are using this mode. You can use both the modes are available in the process. We use this process for welding inconel alloy, because inconel alloy, you know that nickel-based alloy, it is a high temperature alloy, and in the most of the aero engine components, gas turbines, nearly 47% of the components are made up of nickel-based alloys, and 25% components are made of the titanium alloy. So these two alloys can be easily welded using this gas tungsten constrictor arc welding. So we have done a lot of work on tungsten, titanium alloy, and nickel-based alloy. Here I just present only the one case study which we did on the inconel 708 alloy. This work was done for the ISRO, VSS Trivandrum, in collaboration with VSS Trivandrum. So this is about where the inconel 708 alloy is used. High strength with excellent toughness at elevated temperature, excellent creep and stress rupture, excellent corrosion resistance at elevated temperature. These are the advantages of this material. That's why they are using in the aero engine gas turbine components. And here, generally, they are using it gas tungsten arc welding. That's a conventional arc welding process to join these alloys, inconel alloys. When you use these alloys, because of the high heat input and lower arc penetration, which I explained earlier, that leads to the porosity, formation of porosity, distortion, and hard cracking related problems. And also, it leads to the niobium. Niobium is one of the major alloying element segregation that occurs, and it forms the fusion zone with drastically reducing the joint efficiency and leads to the premature failure. So this is the coarse dendritic structure that forms on the welded fusion zone, and here it is a coarse and interconnected law-based phase. That's the law-based phase is the intermetallic phase. It's a brittle phase which forms in the fusion zone during welding of this using this GTAW, conventional TIG welding process, because of the high heat input and lower arc penetration. So to overcome this process, this problem, we utilized this interpulse TIG welding, constricted arc welding. We took the inconel 708 alloy. The base metal details are given in this slide. And if you see here, after welding, the joints were compared with the base metal. The base metal tensile strength is 870 megapascal, and the welded joint after welding it yielded 863 megapascal. That is nearly 99% is the joint efficiency. But failure occurs again in the fusion zone because the fusion zone hardness is little bit lower, and it's the hardness. If you see that the fusion zone is 284 and base metal is 292, at the interface between the fusion zone and the heat up zone, the failure has occurred in this. And also the notch strength ratio is less than 1. That indicates that both the base metal and the welded joint are notch brittle materials. When if you introduce a notch, it will behave like a brittle material. So then we went for the microstructure analysis, and we found that the elemental analysis was done. If you see the niobium phase, and which is responsible for the formation of the Lavis phase in this alloy, and the base metal, it has niobium is 7.65%. But in the Lavis phase, exactly on the Lavis phase, if you measure the composition of the Lavis phase, it has 10.05% of niobium. It is increased nearly some 2.5% increase in the Lavis phase. In the dendritic core, it is 5.57 the niobium content is there available in that. So how to minimize the formation of the niobium phase in the niobium in the Lavis phase. So then we did optimize the parameters using the response surface methodology, and we found that. So if you see here this table, and the tensile properties of the joint, you forget about the top one, tensile properties of the joint. If you use GTAW, that's a conventional TIG welding process, and this is the joint efficiency obtained is only 71%. If you use the gas tungsten constricted arc welding process, the same material in the asphalt condition, it gives 99.2%. It's almost matching with the base material strength. And EB welding, electron beam welding, the literature reported that it is in the EB welding, you can achieve only 91.66%, and laser beam welding also you can achieve only 96%. So this process is much better than the GTAW process, and it is an alternate process to the that EB welding and electron beam welding and laser beam welding process that was proved in this. So what is the reason here is the superior tensile properties is attributed to the grind refinement because there is a pulsating action, and the lower Lavis phase formation, because the Lavis phase formation is disrupted or disturbed by the fluctuating action of the arc, and the refinement observed in the fusion zone. And that's the joint efficiency is higher when compared to the 20 to 30% higher than the conventional TIG welding process. So this process now it is used for joining the titanium alloys as well as internal alloys, and this is used for the repair and refurbishment of aero engine components. That is a very important thing, outcome of this work, and this can be applied for the repair and refurbishment of the aero engine components. And the next one is, I just want to focus on another process, advanced process in the GMAW process. It's known as the rotating arc welding technique. So the rotating arc welding technique, here, electrode rotates in a circular motion. So in the GMAW, you know that there is a wire is fed in the forward direction. So here, the filler wire is rotated. Let's see the clipping. So here you can use no need of exit preparation. Yeah, so the molten droplets are propelled from wire to the base metal in a circular pattern, and this produces a centrifugal force which acts on the molten pool and minimizes the heat input and improves the sidewall fusion and produces minimum heat output. So these are the advantages of this process. We have this process, we have this facility in our center, and the work was done on the RHA steel, rolled homogeneous armor steel, which is used widely in the construction of the battle tanks. This work is supported by CVRD, Compact Vehicle Research and Development Establishment. For welding the armor steel, we use this process. And the thick plates, one of the problems during welding of thick plates is the joint design. We have to go for the V groove or double V groove, single V groove or double V groove. And then position welding, it is impossible to weld out of position in spray transfer mode. And in many cases, we found that when you go for the multi-pass welding, improper sidewall fusion is one of the problem. And especially in the rolled homogeneous armor steel, RHA steel, the heat after zone softening is another problem here. Normally, the heat after zone will have the higher hardness, but here the heat after zone getting softened due to the heat supplied by the process here. Because heat out zone softening occurs, the heat out zone goes below the hardness level of the base metal. Then there is a possibility that the projectile, if it attacks exactly on the heat out zone, that will pass through the base metal. So these are the problems. So here we took conventional MIG welding process, GMAW process, that is referred here as the SCA. SCA means stationary arc. GMW, that's a conventional GMW. REA is rotating arc GMW, that's a new process which you are. So for 18 mm thickness plate, here in the stationary arc, we used 6 passes to complete the full penetration, complete joint fabrication. But in the REA joint, REA process, rotating arc process, we need only 3 passes. Because there is no edge preparation, it is the square bed joint configuration as welded here. That's why the number of passes is reduced here. And if you see the macro structure of this 2 joints, if you see that the well metal area, so the stationary conventional GMW, it is 205 mm square, but in the rotating arc, it is 90 mm square well metal area, because only 3 passes is involved here. And similarly, heat of zone area also reduces from 68.7 mm square to 22.6 mm square. So 1/3, it reduces 1/3. And if you see the number of passes, from 6 passes, it came down to 3 passes. That is mainly because of the cumulative heat input, because each pass and 6 passes, it leads to the 4.6 kilojoules per mm. 3 passes, it requires only 2.13 kilojoules per mm. So total cumulative heat supplied to the material is greatly reduced in this process. So that reflects in the mechanical properties also. If you see that the joint efficiency is 62% in the REA. REA GMW process, but in the conventional GMW, it is only 51%. Because why the joint efficiency is low? Here we used only the austenitic stainless steel filler. Though the base metal is ferritic steel, high strength steel, 1000 to 1100 megapascal tensile strength, but due to the restriction means hydrogen induced cracking and other problem, they suggested to use only the CVRD suggested to use only austenitic stainless steel filler to avoid the hydrogen induced cracking during service. So in the austenitic stainless steel filler, if you use austenitic stainless steel filler, the strength will be joint strength or joint efficiency will be around 50% only. So by this method, the joint efficiency is improved, increased to 51 to 6 to 10% increase is obtained here. So the well metal hardness, if you see that well metal hardness, it is 260 HV and 312 HV. But base metal, if you see that it is a 450 HV, base metal hardness is very high. So that's why they are going for the austenitic stainless steel filler. And there is a microstructure, in both the process, the microstructure is composed of delta ferrite in the plain austenitic matrix. There is no much difference in the phase volume fraction of the delta ferrite, 27% to 25 to 27% only. But the morphology of the delta ferrite is changed because of the stirring action of the rotating action or the centrifugal force acting on the weld pole. In the stationary, the GMAW, so the delta ferrite is globular. But here in the rotating arc, it is a vermicular, the delta ferrite as formed. And similarly, because of the single groove, V groove we are taking, there is an unmixed zone between the well metal region and the heat after zone, UM is that, between that. But here, there is no zone between the well metal and the HAZ because we are using the straight edge or square butt configuration. And this, of course, we can explain all the mechanical properties, mechanical properties of the joints will be weld metal it's nothing but strength and hardness. The strength and hardness is influenced by the microstructure and the grind size, the volume percentage of faces. These three, the morphology, grind size, faces, all those things are controlled by, influenced by the solidification pattern, solid state transformations, inclusions, and gas distribution. So this solidification pattern is influenced by the cooling rate and heat input during welding process. So in the stationary arc process, heat input is higher, 4.63 kilojoules per mm. But in the cumulative heat input, in the rotating arc, we are using only 2.13 kilojoules per mm. That is the reason the cooling is faster, and that affects the morphology of the delta ferrite into the globular, into the vermicular microstructure. So because of that, there is an increase in the 15% higher tensile strength is obtained, and then it is the heat of zone width is minimized to 1.8 millimeter from 3.6, and number of passes also reduced from the 6 passes to 3 passes. So if you see the benefits of this process is, you can go from, in conventional GMAW, you have to use the single V or double V joint configuration. But in the rotating arc, you can go for the what you call the square butt joint configuration. So there is a 40% improvement in productivity and weld cost reduction, because only 3 passes are required, and the weld metal cost is reduced here, and less weld metal is utilized here. Heat of zone also, the width of the heat of zone is also reduced, and that finally heat input is low, the distortion is also reduced here. So these are the advantage of this process. The third one is CMP process. Of course, many of you have heard about this process, CMT, cold metal transfer arc welding technique. So briefly, I'll explain what is cold metal transfer arc welding. I don't want to go into detail. The cold metal, it's not the weld metal is cold. The weld metal is it's a low heat is supplied through the weld metal. So in the conventional, this is also a variant, advanced form of the GMAW, gas metal arc welding process. In this process, in the conventional GMAW process, the wire the filler wire is fed in one direction, in the forward direction. Okay, and the wire melts and it is consumed, and it is continuously fed in forward direction. Forward means moving towards the weld pool. But in the CMT process, what they did was the wire feed is not only in the forward motion, it also in the backward motion. Why they did is, again, as I told in the beginning, the metal transfer, the phenomena involved in the metal transfer is, if you see here, the filler wire, it melts here, the molten droplets forms, and the molten droplets, once it transferred to the, 1 minute. So the molten droplets forms, and between the molten droplets, okay, see, during that time, no need to have the high current. And if you have to, the wire is retracted back again. So once the third stage, the wire is going back again, it was retracted. So here, what they have the two motors. One motor will move the wire forward direction, the other motor will pull back the wire in the backward direction. So this is happening. If you see these clippings, and you can understand, this is the first one is the CMT. You can see the push-pull action is there in the wire, but in the conventional GMW, in the right side, it is only in one direction. So when the filler rod approaches close to the weld pool, heat input will be higher. When the filler rod is retracted, the heat input is reduced here. So this happens alternatively, hot, cold, it is continuous. That's why it is a cold metal transfer. When compared to the conventional MIG welding, the heat supplied in this process is greatly reduced. That is the one advantage of this process. So we use this process for making the additive manufacturing, wire arc additive manufacturing of aluminum cylindrical components. So this is the aluminum alloy, so it's known as the 5356, that's aluminum 5% magnesium alloy. We took as the wire, filler wire, and we used both the process, conventional MIG welding and CMT process. And these are the heat input, and these are the, we have a facility for that to carry out the wire arc additive manufacturing. Using this facility, we made the cylinders of the height of the 150 mm height and the 150 mm diameter, wall thickness of 4 mm. We want to see, because this 150 mm height wall requires nearly some 70 passes, 60 to 70 passes of deposition, one layer after the other. No, you want to deposit. Just we want to see whether the microstructure is uniform from bottom to top. That's why we made, after fabrication, we made this
Participants, kindly bear with this. There is a disturbance in the speaker side, speaker side, process side. Kindly wait. It will be set right. சார் சொல்லுங்க சார் என்னாச்சு வெயிட் பண்ணுறேன் சொல்லிட்டேன் நான் Participants, there is a power failure in the institution. Kindly, there is going to be backup. They are going to make it ready. It will be shortly. It will come back. Kindly wait. Kindly bear with us.
Sir, sharing facility கொடுங்க, because I'm rejoining again.
Rajesh.
Yeah, sir.
Kindly share. திரும்ப சார் கொடுத்துருங்க. Share right side share பண்ணுங்க again.
Okay.
Because I am rejoining again.
Okay, sir. No problem.
Sir, permission given, sir.
Okay. Share.
Sharing.
Sir, can you see the slide?
You are able to see, sir. Please go ahead, sir. Please go ahead, sir.
Okay. Sorry, it's some disturbance.
No problem. Please go ahead, sir. Please.
Yeah, we did we used two processes. One is the GMAW and the other one is CMT for comparison purpose. And if you see the number of deposition to achieve 150 mm height, is 56 in GMW and 56 passes in CMT process. The number of passes remains same, but the heat input per pass is different. 300 kilojoules in the GMW. Here it is only 240 kilojoules, 240 joules per mm. And this is the facility we used, and these are the cylinders we made. And here, if you see that we made this a two portion. One is the top, from 0 to 75 mm, it is bottom portion. From 75 mm to 150, we made this a top portion. So if you see here there is not much difference in the from bottom or top portion. Okay, the tensile strength is. And but if you see that CMT and GMAW, between CMT and GMAW, there is a appreciable variation in the tensile strength. CMT has produced nearly around 250 megapascal tensile strength, but GMAW produced only 220, 224 megapascal. So that difference is there, and that is reflected in the hardness values also. In the GMAW, it is 72 or 70 average, and here it is 85. So 50 HP higher hardness is achieved in the CMT process. So what is the main reason for increase in the hardness as well as the strength is? Then we went for the microstructural analysis. The grinds are finer. One is in the CMT, the fine grind size is formed in the compared to the GMAW because the push-pull action of the filler wire. That means push-pull action of the arc. Arc is going forward and backward. It's a push-pull action. So when you do the push-pull action, there is a fluctuation in the heat input also. When the arc is moving towards the weld pole, the heat supplied more. When you are retracting the arc backward, the heat supplied to the metal is reduced. So there is a fluctuation in the heat input. And in the conventional GMW, there is no push-pull action, only in the forward motion is going. So there the heat input remains constant. And apart from that, that action produces fine grinds. And apart from that, the pores, because in aluminum alloy, porosity is one of the culprit and one of the forms. If you see that the number of pores is greatly minimized in the CMT when compared to the GMW process. So that is the percentage of porosity in the CMT is something around, it's less than 1%, but in the GMW it is higher percentage. So the porosity is less, then the material is more dense and it's more harder and it increases the strength. That is the reason for it. And we compared with the wrought alloy also. We compared these values with the wrought alloy of aluminum, same grade. So it is almost matching with the wrought alloys also. So the CMT process is a preferable process for making wire arc additive components using wire arc additive manufacturing technique. So there are many processes available for wire arc additive manufacturing, like conventional GMAW process, and even people are using a conventional TIG welding process. But this CMT process, because of the lower heat input involved, this produces the dense material, harder material, and stronger material than the other welding processes. So this is a beautiful process for making wire arc additive manufacturing. And the fourth process is FSW, friction stir welding technique. I will quickly go through it. FSW, many people have heard, it's a solid state welding process. And it is we are using a non-consumable electrode. Okay, the non-consumable electrode is used here. The tool, not electrode, it's a tool is used here. So this process was initially invented by the Welding Institute, TWA UK, in 1991. And it was a patented process till 2001. After 2001, many people started working on this process. So basically, this process was developed to weld aluminum alloys, because aluminum alloys, especially high-strength aluminum alloys, are challenging one to weld by MIG welding or TIG welding process because of the hard cracking problem, porosity formation, alloy segregation, partially melted zone. These are the problems normally occur in the fusion welding of aluminum alloys, high-strength aluminum alloys. So this process is basically developed for welding aluminum alloy. So for welding aluminum alloy, you can use high-speed steel as the tool. The tool is the heart of the process. the tool has three portions. One is the top portion is the shank portion, which will go into the machine, fit into the machine, and below that there is the shoulder region. That shoulder and below the shoulder there is a pin region. It is a dotted in the form of dotted one. So here the design of the tool is very important. You cannot use one tool for all the plate thicknesses. If you based on the plate thicknesses, you have to make the tools. For example, if you want to weld, okay, 6 millimeter thick aluminum sheet, then you have to make the specific tool for this 6 millimeter thick aluminum sheet. So normally the pin diameter is equal to the plate thickness, and the shoulder diameter is normally 2.5 to 3 times the pin plate thickness. 6 millimeter plate thickness, shoulder diameter is 18 millimeter, the pin diameter is 6 millimeter, and the pin length is shorter, 1 mm or 0.5 mm shorter than the plate thickness. So you have to make a tool and you have to use it. So one important thing is this typical characteristics feature of this process is, so like other welding process, you have unaffected parent metal away from the weld zone. And nearer to the weld zone, adjacent to the weld metal region, you have the heat after zone. This is true in all the cases. But in this process, there is one more region is known as the TMAS region, thermomechanical affected zone. That is, it is in between the weld zone and the HAZ, heat after zone. That thermomechanical affected zone is the typical characteristic feature of this process. So the D region in this diagram, that is known as the still zone, or it is also called as the dynamically recrystallized zone. So dynamic recrystallization takes place during welding process, and that produces very, very fine grinds in the still zone region. Okay, so if you see this animation, the tool rotates at rotational speed, plasticize the material, and then it stills the material. And once that is established, you can move the tool forward direction. So here also a lot of parameters you have to optimize: tool rotational speed, welding speed, axial force, which is acting through the tool, and then tool pin profile, tool shoulder diameter, tool tilt angle. These are the parameters. So if you use again here you have to optimize these parameters to get the optimum quality of the weld. So because if you don't do the optimization, what will happen? High heat generation will lead to this type of defects: turbulent material flow, grind coarsening, excess splash formation, and piping defect, tunnel defect. All these defects will happen. And if the heat generation is very low, then the material will not flow vertically, and it will also lead to the problem like pinholes, hissing on, lasers, cracks, all those things will form. So one needs to optimize the process parameters to get the defect-free weld. But as on today, for aluminum alloys and magnesium alloys, the FSW process is well established. Optimized parameter is available for all the grades of aluminum alloys and magnesium alloys. For other materials, people are working. So now, based on the success that experienced in the soft metals or low melting materials like aluminum, magnesium, copper, the researchers used this process to weld the high melting materials, high melting temperature materials like steels, carbon steel, stainless steels, titanium alloys, and nickel-based alloys. We also did one work on the IF steel. We have done a lot of work. One case study I am presenting here. This IF steel is widely used in the automobile sector because of high ductility. This is the microstructure. It's full of ferrite grinds. Why it is called interstitial free steel? Because carbon is almost 0.002. Okay, if it becomes 0, it is iron, because we will need to keep some carbon. So interstitial element, one of the interstitial element is carbon. It is almost kept 0. Okay, close to 0, 0.002. And this is a microstructure. Grind size, average grind size is only 20 microns. And this steel was welded using this process, friction steel welding process. One of my students, Dr. Lakshmanaran, did this work some time back. And here the challenge is you cannot use the high-speed steel tool material. So you have to develop a tool for withstanding, you see the tool condition, it has to withstand this condition, hot condition. And the pin profile and shoulder profile should not be lost. There should not be any tool wear. So you have to select the materials which can withstand this temperature and also the forces at this temperature. So tungsten-based alloy is one option, and molybdenum-based alloy is another option, and the tungsten rhenium alloy, PCBN is the best option for going for this tool, to make the tools for the welding, friction stir welding of high melting temperature materials. So here also we used FSW and GTAW TIG welding process for joining IF steel. And you see here, this slide is very important. So the top one is the fusion zone. Fusion zone is when you use the TIG welding process, the fusion zone microstructure is shown here. The average grind size is 80 microns. But fusion, the stir zone of the FSW, you see the grinds become finer. The average grind size is 5 microns here. So when you use TIG welding, the grinds are grown because of the high heat input involved in the TIG welding process. But here in the stir zone, there is no melting at all, only the plasticizing, and there is a dynamic recrystallization takes place. Because of that, grinds become finer and finer here. And this is one method, viable method to produce near nano grind bulk materials. Near nano grind bulk materials. We are also trying that to produce near nano, because nano means the grind size should be less than 100 micron, 100 nanometers, but we achieved only 500 nanometers. Okay, that's a near nano materials can be achieved by this process. And the heat of the zone microstructure, if you see that in the TIG welding, it is 105 microns, the average grind size in the heat of the zone, because grind growth taking place. But the base metal microstructure is only 20 microns. And the FSW in the heat of the zone, it is 20 microns. So because of the stirring action, because of the less heat input, this process gives better performance. If you see that mechanical properties, again tensile strength, the base metal tensile strength is 282 megapascal, but TIG welder joints gave only yielded only 208 megapascal, but friction stir joints yielded 274 megapascal, just few 10 megapascal lower than the base metal strength. So that means if you see that joint efficiency is 74% in TIG welding, 97% we have achieved in the FSW. But in TIG welding, the problem is we have to use the filler wire, we have to use the shielding gas, and you have to prepare the edge preparation. But here there is no shielding gas, there is no need of filler wire, there is no need of the edge preparation, and this process is no smoke, no fumes, no radiation, nothing is there. That's why this process is known as the green welding process or clean welding process. Not only the process is clean, and also the performance of the joints are superior compared to the conventional welding processes. And this process, FSW, has enormous potential to use in different conditions. It is very good process for joining similar and dissimilar materials. Friction stir processing to refine the grinds. This is an ideal process. Friction stir spot welding. Now, many of the auto industries are replacing rivet thread joints by friction stir spot welding. Friction surfacing is another area, and surface composites we can develop. And near nano grind, which I mentioned, it is possible, viable, using this method, you can produce near nano grind materials. And the last process today is solid phase diffusion bonding. Of course, the diffusion bonding also solid state welding process, but it is a slow process. And here there are different stages is there. Initially, here you can the contact is established, because whatever you do the polishing and other thing, there is the asperities on the surface. So peaks and peaks will contact, and valley there is a gap in between that. This process involves pressure and the temperature you have to apply, and you have to give sufficient time also. So bonding pressure, the pressure should be high enough to ensure high contact between the two joining surfaces, but it should not exceed yield strength, because if the yield strength, if the bonding pressure exceeds the yield strength of the material, then material get deformed. So the shape and dimensions will get affected. And bonding temperature, again, the bonding temperature should be 50 to 70% of the melting point, because you should not go very high temperature also, because that leads to the recrystallization and other the problem will come. So it should be below the recrystallization temperature. And holding time. So you have to give sufficient time, because it's a slow process, and you have to give a minimum of 30 minutes, maximum of 2 hours also required to get the good quality bonding. And the surface roughness, that is also very important. You have to prepare the surfaces, and it should be finished to the surface roughness of 0.4 microns. And the plates to be bonded should be stacked one over the other, and that should be kept in a vacuum furnace, and you have to fix the temperature. The furnace temperature raises, and slowly the bonding takes place. The grinds will grow and they will combine together. And if you do similar materials, bonding of similar materials, then you will not find any interface between the materials here. Right. So we recently did a case study that's for GE. We did a one project, mini project for them. Fabrication of heat exchanger stacks. So the compact heat exchanger, it's not the power plant heat exchanger. It is the used in the electronic industry, small heat exchangers. The electronic devices and electronic components are used extensively. They are using this type of compact heat exchangers. There are 3 types of heat exchangers: printed circuit heat exchangers, formed plate heat exchangers, and hybrid heat exchangers. So in this case study, we tried to make printed circuit heat exchangers being okay. So I don't want to go into the details about the other thing. So heat exchangers we used here in Inconel 625 thin sheets having thickness of 2.5 millimeter, and 50 mm by 50 mm we made the sheets. In the sheet, for the fluid flow, we produce the keyways using the grinding process, and then it is polished, and then it is stacked one over the other. So 10 plates of each 2.5 mm are stacked one over the other. So by doing that, after arrangement, you have the channels. Through the channels, the fluid will go, the coolant. You can pass through the coolant through it. Whatever the heat generated on the top, that coolant will absorb the heat. So one end is the cool end, the other end is the hot end. So like that, this is used in the electronic industry. So all these stacks, 10 sheets are stacked in the vacuum furnace, diffusion bonding press. Then the temperature is fixed and the pressure is applied and the sufficient time was given. And this is the facility we have, the high temperature diffusion bonding facility we have in our center. And we made the heat exchanger stacks using this process. Then we did the study. We want to see the bonding strength. We want to see the microstructural features, and we slice the specimen to study all these characteristics. And it's not easy because first we have to identify the feasible range of temperature. So less than 900 degrees centigrade, no bonding has occurred. And above 1150 degrees centigrade, stacks bonded with the die top plate. Okay, that is the problem. So in between 900 to 1150, the bonding is quality bonding we achieved. Similarly, the pressure, 30 bar, less than 30 bar, no bonding has occurred. Above 70 bars, the stacks again bonded with the die plate. So that's a deformation takes place, and they bonded with the die plates. And holding time, less than 100 minutes, no bonding. If you use more than 140 minutes, again, the bonding is taking place here. So within this range, within this range of temperature, pressure, and holding time, we need to optimize. And again, we use the statistical tools, and also we constructed the diagram. That's a processing map. You can say it is a processing map. Temperature versus holding time, temperature versus the pressure versus holding time. And within that window, okay, the blue color window, if you select any parameter, okay, temperature and pressure and holding time, you will get a bonding. But if you select the parameters outside the window, if you select the parameters, then the bonding will not occur. So this kind of diagrams will helpful to the engineers. So they don't need to do trials. By using this diagram as a reference map, they can select the optimum parameter. But within this range, within this domain, okay, processing map, where the maximum strength will happen. That we used again the RSM and we found that. So what is the effect of temperature? If you see that 4 different microstructure and 4 different temperature we used, and 950 is a clear gap between the top and bottom plate. In the last one, 1100 degrees centigrade, there is no gap. It's completely closed in the diffusion bonding. So temperature is having effect on that. So we have to choose right temperature. And similarly, pressure also, no? So in the low pressure 40 bar, you see that there is a gap still, air gap is there between the top plate and the bottom plate. But in the 70 bar and 60 bars, the completely closed, there's a bonding, complete perfect bonding has occurred in that. And so we optimize the parameters using RSM and also compared with the experimental results. And we are able to make, okay, we are able to make the compact heat exchangers using this method, diffusion bonding method. And the work is going on. We are trying to different profiles and different configurations of the compact exchanges. We are doing it. And this is the ideal process, not only for the similar material, for dissimilar material also. This is the ideal process. Only problem is the vacuum furnace size will limit the component size. And another thing is it's a slow process. Minimum you require 6 hours for 1 hour for heating, 1 hour for cooling, for maintaining the temperature for 2 hours. So it requires one product. To produce one product, it requires 6 hours. But there's no other way. Only few components are to be made using only this process. So with this, I'll come to the final phase of my presentation. This is a brief introduction about my center because many of you are new to this about my center. And the center was established, C Major was established in 2008. We have 10 labs in our center. And we are working on 3 different areas. That is materials joining is the major one. And then we have surface engineering, we are working. And third one is advanced materials. So these are the 3 areas we are working. And for materials joining field, we have these facilities, welding facilities are there. Except electron beam welding, we have almost all the facilities here. Most of them are working, maybe 1 or 2 are under maintenance. And this is the photograph of facilities available in materials joining and surface engineering. That's another area we used to work. Thermal spray coating and the other corrosion resistance coating, wear resistance coating, thermal barrier coating, oxidation resistance coating. So we are working on different coatings using thermal spray. We have very good thermal spray lab. And the tribology lab and corrosion labs are there. Instruments are there to carry out. And these are the photographs of facilities of surface engineering. And the testing and characterization is another facility. We have basic facilities are there for the testing and characterization. So finally, I wish to thank because this is not the work was mostly done by my students. So this is my duty to acknowledge their contributions. I wish to thank Professor Malarvidi, who is working on spin arc welding technique, and Dr. P. Sivaraj, who is working on the friction stir welding, and Tushar Sonar, and who worked on the interpol stick welding, and Shankar, again, he worked on the rotating arc welding. Prasanna, Nagasai Prasanna, who did work on the wire arc manufacturing. Dr. Lakshmi Narayanan, so he worked on the IF steel, friction stir welding of IF steel, and Mr. Suresh Babu, who is a research scholar who did the work on the solid state diffusion bonding. So all these works are funded by different funding agencies. I want to thank them, ISRO, DRDO, DST, and SCRP. So finally, I wish to thank all the participants who are passionate enough to listen to my talk. So maybe there is another 10 minutes, so I am ready to answer to your questions. If you have any clarifications, please, you can ask me. Thank you.
Thank you, sir. It was an excellent talk by you. Really, we imbibed and very good thoughts from you for the emerging technology processes of welding. That is high productivity, high performance in the emerging materials. Really, it was an eye opener to all of us. Thank you so much. Thank you so much. Now, participants, you can ask questions to us, sir. Yeah. You can unshare the screen, sir, so that the people will come on platform and ask questions.
So nearly it's more than 60 participants are there. Yeah, yes.
It went
Any
up to
clarification?
83, sir. 80. Yeah, yeah.
Yeah, okay.
Participants, you have any queries, you can ask to sir.
Sir, good evening.
Yeah.
Yes.
Yeah, this is from Switzerland Energy Limited, sir. Thanks for your
Yes.
service, sir.
Yes.
Thank you, sir. I am working under your guidance scholar through Gopal, sir.
Yeah. Yes.
Sir, just I am having a basic question, sir. Sir, you are saying about that static and rotating arc GMW process.
Yeah.
My basic question is that, sir, in rotating arc GMW, that is the holder itself, it is rotating, right, sir?
Not holder. It's only the wire is rotating.
Only wire.
Wire, because they have a specific arrangement to rotate the wire. There is a motor on the top of the torch. So the wire is rotated. Not the head. The wire is rotated.
Okay, sir. Okay, sir. I got it. Thank you.
That is, yeah. The torch is it's a stationary only. The torch body is stationary only. We are not rotating the torch body. In the you have in the TIG welding, that type of arrangement is there. There is a magnetic arc oscillation. So there also no the torch is stationary. Only the magnetic field will be changing. But here it is the wire is rotated. The pillar wire is rotated.
Okay, sir. Okay, sir. I got it. No, sir. Because I thought it's differently. Because we can do that during. It's a kind of weaving. So
Weaving.
we
Yeah,
do that manually. Right,
yeah, that is possible. But here no, it rotates at even the minimum rotational speed is 600 RPM. Maximum you can go up to 2000 RPM. So you cannot do it by hand.
Yes,
600
yes,
revolution per minute. That is not possible by manually. So here, because of motor rotates, the filler wire rotates at a higher RPM.
Okay, sir. Thanks, sir. Thanks.
So really, it is a very useful webinar because Dr. Selvaraj and his team, Institution of Engineers and IAW, they are continuously, doing. That's a very noble cause because not only on welding, he is inviting many people on different topics. I attended few lectures, but it's unable to attend all the lectures. But it's all the lectures. No, if you see that the title of lectures, talk, it is really informative and useful to the society, and they are doing a noble service to the society, especially the engineering society, scientific community, and free of cost. That is very important. Okay, it's very important.
Thank you,
So
sir.
I
Thank you, sir,
appreciate
for the
the.
appreciation. Thank you. So with all people like you support only, it's going on. Thank you so much.
Okay.
Thank you so much. So I want to tell under Professor Dr. B. Balasubramanian sir, I did my doctorate recently. I need to thank in front of all of our participants. Also, he's for past 5 years he's a top 2% scientist. He's maintaining that, and we are all proud to have you today, sir. Thank you so much. Really, we are honored by your talk. Really, the talk was excellent, sir. We enjoyed your talk. Thank you so much.
Okay.
Really,
Actually,
the
the
meet,
yeah, top 2% scientist and all know it is contributions of my students. I am just only a driving force or guiding force, but they are the real field workers, even like Dr. Selvaraj, So he has published some 5 papers now in the Scopus Index Journal. So though I have given facility, guidance, and work plan, everything, but the student has to work. So that's why I dedicate whatever I got recognition, the recognition goes to equally shared with my students. So they are the field workers. They are doing the work. I am getting the credit. But I am giving some facilities for them, infrastructure, some guidance and other things I am giving, ideas I am giving, problem I am giving. So for some financial support I am giving. So it is a mutual contribution of my students and myself. So I thank my students.
Thank you, sir. All you are behind us. You are motivating force for us behind us. That's all. Thank you. Thank you. Now, participants, if you have any more questions, you can ask. Otherwise, we move on to the next agenda. Kindly wait, sir. Still, vote of thanks. Kindly wait, sir. Kindly wait.
Yeah. I will wait. No problem.
Okay.
Any message is there in this? Any question is there in the
There
chat box?
a lot of appreciations put on the chat box, sir. That I'll
Okay.
send to you, sir. A lot of appreciations.
Okay.
More than 20 appreciations or 20-25 appreciations are there for you. Yeah. Next week there is an interesting topic again, 9-12, as our professor told. 9-12 we have got an interesting talk, that is strategies for continuous career growth in the dynamic IT sector. It's going to be delivered by Ramesh Babu V, Head COE and Legacy Monetization and Automation, Emphasis Limited, DL of IT Park at Punamalli Road. It's going to be, he's an experienced person, he is owning a MNC company, and it is a young budding engineers, it will be very much useful. I request all of you to join for next week's program. We, as usual, we will circulate through our email as well as our WhatsApp message. Thank you for joining. Thank you. I see some Sangu from UAE has joined, and other people, Nanitha from Nepal. Throughout India, people have joined. Many people have joined. Thank you for all of them. Now moving on to the next agenda. Rajesh.
Yes, sir.
அந்த இவரு சார் சுமேகா வெல்டிங் அவரோட வீடியோ ஆன் பண்ணி விடுங்க, வீடியோவும் ஆடியோ ஆன் பண்ணுங்க.
Okay, sir.
ஐ அம் காலிங் ஃபார் வாட் தேங்க்ஸ்.
Okay, sir. Okay, sir.
I call upon Mr. Suresh, Engineer Suresh Kumar is a chairman of Indian Soap Welding Tichinapalli branch. I request him to propose vote of thanks. Over to Engineer Suresh Kumar.
Good evening to all of you, sir. I would like to express my gratitude for the opportunity to me to deliver the vote of thanks. Our first and foremost thanksgiving goes to the Almighty God, the creator of you and me, for what we have and what we don't have. Dr. R. Silvaraj, past chairman of the IEW, is a man blended with industrial experience and a good academic profile. He is organizing the Tuesday events regularly. Our gratitude to you, sir. Dr. Kevin R. Kumar,
Thank you, sir.
chairman of IEI Tichinapalli Local Center, introduced, welcomed the today audience. I record our sincere gratitude to you, sir. Mr. Ramachandran, Secretary of IAW Tichinapalli branch, he is introduced today's speaker and worked towards this program. Gratitude to you, sir. Dr. V. Balasubramanian is the speaker of today's topic, high performance and high productivity technologies for joining emerging materials. There have been so many good points. They are really coming from the professionalism, ability to pull the knowledge, and communicate clearly and precisely. I am actually glad of this topic brought up. I express our sincere thanks to you, sir, for your stewardship, support, vision, and commitment. I thank you all the 79 distinguished participants, office staffs of IEI Trisabli Local Center, and everyone showing their interest to participate this program. Once again, I thank one and all present here. Thank you, sir.
Thank you, Suresh Kumar, sir.
Thank you, sir. Thank you for excellent show, sir. Thank you, sir. Thank you, Dr. VB, sir, for
Thank you.
a useful presentation to all of us. Thank you so much. We
Okay.
enjoyed your presentation, sir.
Okay.
So we'll send a separate thanks letter to you, sir, for your today's
Thank you.
talk.
Thank
so
you.
much.
Thank you,
So,
Samaraj. Thank you all. Thank you
yes,
for
sir.
joining.
So
We'll
thank you,
meet
sir.
again.
Good night, sir. Good night.
So for the participants, I actually I don't know how many of you left. So there is a national welding seminar scheduled to be held in Cochin from 18, 19, 20 December. If somebody is interested, you can contact me or you can contact Dr. Saluraj or Dr. Mr. Suresh Kumar for the details. So it is a mega event, national welding seminar scheduled to be held in Cochin from 18, 19, 20 December 2025. I invite all of you. Somebody interested, you can contact me. Or Dr. Salvaraj, you can contact. Thank you, sir.
Sure, sir. Thank you, sir. I shall circulate to all the people, all our members.
Thank you.
Sure, sir.
Thank you.
Thank you, sir. Thank you, sir. Good night, sir. Good night, sir. So for the participants, the feedback link is posted. You can fill up the feedback link with your name and your email ID correctly, so you'll get your participants in inbox within few seconds. Maybe, sir. Thank you, sir. Good night, sir. Good night, sir. We call up the day, sir. Thank you, sir.